So today's presentation webinar is titled "Can we calibrate in one fluid and operate in another?" It's quite a common question that I'm asked. Been asked it several times over the years, both from customers and even just end users as well. So hopefully I can provide some information on that today, and then some of the work that we're doing here at NEL in that regard. So the agenda for today: meet the speaker, so a bit about myself, so a quick bio, then background to the webinar, then we've got some meter types that I'm going to describe, and then some experiences, and then recommendations and conclusions, and then we'll follow up with some questions and answer session at the end. So today's webinar should be approximately around about 45 minutes in duration. That's the kind of time frame I suspect we're looking at, so hopefully won't keep you all too long, and you'll be away within the hour. So as Amelia says, my name is Dr. Chris Mills, a senior consultant here at NEL, predominantly working in flow measurement consultancy and R&D projects such as the BEIS government funded flow programme work, and also European metrology research. I've worked at TÜV National Engineering Laboratory for 14 years, or just over 14 years now. Recently completed my engineering doctorate at Coventry University. I say recently, it was about 2 years ago now, so maybe I could update my bio and drop the recently, but still like to mention it, and occasionally drop in the doctor as well at the start of my name. It's the only time I really get to use it, if I'm being honest. So in terms of background, as I said, the title of this webinar is "Can we calibrate in one fluid and operate in another?" Now, there's a few parts to that question, depending how you focus on it or interpret that question. If you send your flow meter to a calibration laboratory anywhere, it doesn't need to just be NEL. We are, of course, the designated institute for flow in the United Kingdom. If you send your meter to a calibration laboratory, well, you're already going to be calibrating a different fluid into the one that you operate in. It's highly unlikely that it's going to be a perfect match. It's almost certainly not going to be the case, because most laboratories either use substitute fluids, or even if they do use things like natural gas, it will potentially have a different composition, or certainly will have a different composition. So if you do send your meter to another laboratory, then already you're calibrating in one fluid and then using it in another. However, that isn't quite what I mean by the premise of this webinar, and we're talking about completely different fluid types. So can you calibrate in one fluid and then use it in a completely different, such as a high viscosity fluid, or say LNG, for example. So that leads me to the first slide here on the background. Some of the work I've been completing in the past 18 months or so is around flow measurement requirements for CO2. I recently just co-authored a journal paper on the flow measurement challenges for CO2. That will hopefully be available soon. It's just undergoing peer reviews just now and should be published shortly. And there's a few challenges around that. One of the main challenges, or one of the things that I've been discussing with colleagues and other interested parties, is whether you can calibrate in one fluid, such as water or nitrogen gas, for example, depending on the CO2 fluid medium, whether it is liquid or whether it's liquid or gas. And at present, I'll be honest, we don't have all the answers for that just now, and that partly stems from a lack of traceable flow facilities. So as I say here, there's only a limited number of traceable flow laboratories in the world that can offer calibrations with challenging fluid properties. For CO2, it's actually a lot more difficult. There's no liquid CO2 or fully traceable accredited laboratories in the world at present. So that's a real hindrance for CCUS schemes. There are some facilities that can offer CO2 calibrations in gas, but there aren't a lot. And if anything, we certainly need more for the uptake of CCUS schemes to provide that confidence in the flow measurement. So just now there's still a question as to whether we need to build these new facilities for gas CO2 and liquid CO2, or can we potentially calibrate in water, which is readily available in a lot of calibration laboratories, or nitrogen gas, for example, again, freely available in a lot of calibration laboratories, and then use them in CO2 with a higher uncertainty. So for example, calibrate in water at
ambient conditions and then use them at elevated conditions with a completely different fluid, CO2, what kind of uncertainty would you expect? But that's a very difficult question to ask without real data from traceable laboratories. So that is the question that's to be asked. But it's not just CO2, that's not the whole premise of this webinar. I want to also discuss other fluids as well, the whole idea of calibrating in one fluid and operating in another. So another challenging fluid is LNG, liquefied natural gas. And obviously there's a substantial market, it's far more developed than say current CCUS schemes. There's in the region of about under 20 CCUS schemes currently active in the world, and most of them are located in North America, whereas LNG is freely traded just now. There's a lot of different LNG cargo ships. It currently is measured. However, there's a lack again of traceable accredited laboratories. There is one in the VSL facility in the Netherlands, a facility for the calibration of LNG flow meters, but there's not a lot. A lot of the work they're looking at just now is whether you do need a substantial large LNG calibration laboratory, or can certain meters be calibrated in a different fluid as well. So there is that calibration transferability that's been explored as well as part of their facility. Another fluid that's of interest is high viscosity fluids. So I've got here a heavy oil. Here at NEL we have a high viscosity flow facility that goes up to 2000 centipoise. We've completed a fair amount of work regarding low viscosity and high viscosity calibrations and how the effect of viscosity on common flow meters. So in terms of the background, sorry, I'm just waiting for my slide to load here. Not sure if you're seeing a blank screen or whether it has loaded. Just bear with me a second. Just wait for it to load a second. Yes, excellent. It's loaded now. Apologies for that. I think maybe I've made the slide a little too complicated with animation. So that should have animated through, but I think we are moving forward now. Oops, going backwards again. Bear with me. This is why you shouldn't include animation in slides. It just it fails when you don't expect it to. So in terms of NEL's experience with the calibration of different fluids, I've been at NEL for 14 years, but going back 16 years, so back to 2006, 2 years before I started, NEL started to look at heavy oil, high viscosity fluids. They modified one of the facilities to operate up to 300 centipoise and looked at the effects of that on common flow meters. We've seen that there was a viscosity effect, and we actually created a GIP when I started in 2008. We launched a GIP into high viscosity fluids. We also decided that there was a requirement for higher viscosities, so we modified our facility via UK government funding from the flow programme to operate up to 2000 centipoise. Completed the GIP up to 600 centipoise, and we found that there was a significant viscosity effect with a variety of flow meters. That answered the question about viscosity. There was always a question around elevated temperatures, especially with respect to Coriolis meters. And in 2010, some customers who were looking at a new field in the North Sea back in 2010, or an upgrade to a facility, it was operating at high temperature, previously used turbine meters, and they were switching them out to Coriolis meters, but they were operating up at 70 degrees Celsius. And they wanted to know that whether elevated temperature affected the performance of Coriolis meters. So we did some initial trials in our facility up to 60 degrees, because that's what maximum temperature we could achieve at that time. And we found that there was a slight temperature effect, not as large as viscosity, but certainly an effect nonetheless. So that gave me the idea to create another joint industry project, the GIP, this time focusing purely on Coriolis meters with respect to process effects. So launched the GIP looking at high viscosity fluids, elevated temperatures and elevated pressures. We completed that GIP in 2 years' time. We had 12 sponsors. It was an extremely successful GIP. We had 3 different Coriolis manufacturers, each supplying 2 different sizes of meters, so 6 meters in total. And there was various different outcomes, but the main outcome was that there was a requirement for a new flow facility that could calibrate flow meters at process conditions, so as close to service conditions as possible with respect to temperature and pressure, due to those temperature and pressure effects that I've already mentioned. So we, again, applied for UK government funding in 2014 and designed and built that facility within around about 18 months' time, had that facility ready. It was extremely successful and it's been operating since then. It's now 6 years later and it's fully operational. We have a lot of commercial data from it and we've completed a lot of interesting research projects as well. So I'll tell you a bit more about that facility. It's known as the Elevated Pressure and Temperature Facility. It's EPAT also, it's known as, so that's Elevated Pressure and Temperature, EPAT, Liquid Flow Facility. So here's a schematic of it here just now. In terms of the facility, we use a small volume prover as a primary. It's a 60 litre small volume prover. We have 3 different helical turbine secondary reference meters. So they are calibrated against the prover and used as master meters ultimately. It's a closed loop system, so as you can see we have a buffer vessel that fills the line once the device under test. So let's say a Coriolis meter is installed in the test section here. The line is filled, we've got 2 main flow pumps, an inline heat exchanger, a pressurization unit to achieve the required pressure, heat exchanger for the required temperature. We flow round through the prover, through the required reference meter depending upon the flow rate, and then round depending on which test section the meter is installed, flow through and then continuously flow round. So a closed loop system. There's various benefits to that. Temperature and pressure are far more stable. We need a much smaller volume than we would if it was a stop-start system or a gravimetric system, for example. It has a pressure range from 4 to 100 bar. So this is a liquid flow facility that got up to 100 bar. It's one of the only ones in the world that can operate at such elevated pressures. And we operate from 20 degrees to 80 degrees Celsius. So again, extremely high temperatures, high pressures. The temperature can be kept stable for whole calibration within plus or minus 0.5 degrees C, and pressure within plus or minus 0.25 bar for the entire calibration. So extremely stable temperature and pressure. The flow range operates from 0.5 to 100 litres per second. And crucially, the measurement uncertainty for mass and volume is 0.08%. Now you may know, calibrate a lot of Coriolis meters, which are mass-based devices, and our references are volumetric. We have a volumetric prover and a volumetric reference helical turbine system. That means that density is an extremely important component. So we have characterised our fluids with respect to temperature and pressure across the entire operating range and have very stable fluid properties which we monitor, and we have a very low measurement uncertainty for the density. That allows us to then calibrate with respect to both mass and volume for an uncertainty of 0.08% at the 95% confidence level. Now, it's not the only facility we have here at NEL. We also have dry gas facilities. We have an advanced multi-phase flow facility. We can operate with 3 phases. But we also have an oil flow facility as well. Don't have quite as nice a schematic for this one, but this is our national standards for oil flow. It has a gravimetric primary system, which is this weigh tank system here. We actually have 4 of varying different sizes depending upon the flow rate at which we're operating at. We use positive displacement reference meters. So these are pre-calibrated against the weigh tank for a given viscosity and temperature. So we can operate start-stop, basically that's flowing through into the weigh tank, or we can operate in recirculation mode using these master meters that are pre-calibrated. Now the pressure is much lower. Historically, most calibration
facilities for liquid operate at low pressure, because pressure wasn't deemed to be a significant influence on meter performance. We now know for certain flow meters it is, and if you are operating at high pressure, then you should ideally characterise your meter for pressure. But most liquid flow facilities are relatively low pressure, so we operate 1 to 4 bar. Temperature, again, fairly similar, 15 to 50 degrees Celsius. In the flow range, it's larger than the EPAT facility. We can go from 0.05 to 200 litres per second. We're fully accredited. Our primary uncertainty is lower. It's 0.03% at the net 5% confidence level, so that's going to the weigh tank. And if we use our secondary reference master meters, the uncertainty for mass and volume, similar to EPAT, is 0.08% at the net 5% confidence level. So that's a bit about the background in terms of our facilities. As already mentioned, there's a lack of CO2 calibration facilities with primary standard traceability in both the UK and globally. However, it's critical to establish CO2 calibration facilities that can provide independent traceability for flow meters backed by primary national standards. So this lack of facilities ultimately means we don't have confidence in the performance of flow meters with CO2. As the UK's designated institute for flow measurement, NEL are moving to address this gap in flow measurement capability. So we have applied for funding. We're aiming to have a gas CO2 flow loop and a liquid CO2 flow loop. We're actually already underway with the gas CO2 flow loop just now, upgrading our existing gas flow loop to accommodate CO2, hoping to have that complete in the next year. And we also have plans for a liquid CO2 flow loop. We've developed the pre-feed just now, so we have a concept design, we're in the pre-feed, and we're exploring funding opportunities for a liquid CO2 flow loop. So will hopefully help answer some of those questions as to whether you can calibrate in one fluid and operate in another. Even if that is the case, it will still have a relatively high uncertainty. As the CCUS schemes become more widespread and the carbon price increases, there's potential that the measurement uncertainty for CO2 will decrease, and as such, even although you potentially could calibrate in one fluid and using CO2, to get the required low measurement uncertainty, you would ideally want to calibrate in CO2. So there still potentially will be a requirement for a gas CO2 flow loop and a liquid CO2 flow loop, irrespective of whether you can calibrate in one fluid and operate in another. So that's the background. The question still remains, however, can flow meters be calibrated with one fluid and then successfully operated in service with a higher uncertainty? So yes, there's no reason why you couldn't calibrate a flow meter in one fluid and use it in another, but certainly straight away it'll have a higher uncertainty. And crucially, what is that uncertainty? How do we know, and how will we know eventually? What steps have to be taken for industry to be aware of what the uncertainty would be if you calibrate in one fluid and then use it in a completely different fluid? So before we go into too much detail, it's worth discussing the actual meter types we're talking about here, because not all flow meters can be calibrated in one fluid and used in another, simply just due to their design characteristics. So in terms of meter types, I have turbine meters here, so a fairly common flow meter. I'm sure most people are aware of how a turbine meter operates, so I won't go into too much detail. So as the flow passes across the turbine, spinning the device, you've got a pickup that picks up the number of pulses via the rotations, which is proportional to the velocity. From that you can get the volumetric flow rate. Now, you get liquid turbine meters, but you also get gas turbine meters, and ultimately a liquid turbine meter should only be used in liquid flow, and a gas turbine meter should only be used in gas flow. So straight away, you cannot calibrate a gas turbine meter in water and use it successfully. Common knowledge, but I just wanted to drive that point home. It's not applicable for all meter types. What about PD meters? Well, again, it's very similar to turbine meters. You get liquid PD meters and you get gas PD meters, and they can only be used in the fluid that they were designed for. So liquid PD meters should be used in liquid, gas PD meters used in gas. So again, you cannot calibrate a gas PD meter in water, depending upon the components of which it was made.
Then we have differential pressure meters. Now these are different, there's no moving parts here. We're discussing DP meters such as an orifice plate, venturi, wedge, cone meter. They have no moving parts and they actually are suitable for both liquid and gas use, depending upon your differential pressure transmitters. You have to make sure they're suitable for liquid or gas use, or both, depending on which fluid that you're using. But there should be no reason you couldn't use a differential pressure meter in water and then use it in gas as well. So DP meters, different from turbine and PD, they can be used in both fluids. Now, what about the more newer, we call them? Let's say these are more historical type flow meters, and then we're looking at some of the newer technologies. One of the more common ones is ultrasonic meter. Now again, you get gas ultrasonic meters and you get liquid ultrasonic meters, but again, they are designed purely for that fluid. So you have a liquid ultrasonic, shouldn't be used with gas, and the same is true for a gas ultrasonic, shouldn't be used with liquid. So due to the design, different transducers ultimately operating different frequencies, they're not suitable. So again, you couldn't calibrate an ultrasonic meter in water and then successfully use it with natural gas, which is a common question we get asked, but it's not possible. However, the other newer technology, extremely popular meter, at least 90% of the meters we calibrate in the air now, Coriolis meters, they come in one device that is suitable for both gas and liquid use. So a Coriolis meter potentially could be calibrated in water and then used in gas. So that's the type of device we'd also be interested in exploring with respect to LNG or liquid CO2. Could you calibrate it in water and use it in gas CO2? Could you use it with liquid CO2? Could you use it with LNG and other challenging fluid properties? Well, some of the experiences I want to share with you that we have from some of our research here at NEL. Now, I want to stress, I've mentioned CO2 a few times, and I've ultimately only really mentioned two phases. I've mentioned gas phase and liquid phase. Now, gas is distinct. Liquid, we're actually encompassing one facility. When I term it as liquid CO2, there's actually other phases. So we'd be looking at liquid dense, and also supercritical CO2. So we'd also be looking to design, and we've got a concept design already for it, for a facility that includes those three liquid phases as I'm terming them. So liquid dense, and supercritical would all be one facility, just with a different operating temperature and pressure range. So it would be a really wide operating temperature range. We'd increase the pressure, and that would get us into that supercritical phase, which has its own challenges, obviously. In terms of experiences, what I have here is just some kerosene, so kerosene data for a Coriolis meter. So this is what are termed uncorrected low viscosity data. So on the x-axis, I have reference flow rate. On the y-axis, I have mass flow rate error. So that is a deviation from the Coriolis meter compared to our reference. In this case, the calorimetric reference system that we have here at NEL. And we have four different data sets. We have kerosene at four temperatures, which gives us four different viscosities, although there's very little variation between them because kerosene being a very light, low viscosity fluid, it doesn't change viscosity much with respect to temperature because it already is quite a light fluid. You can see we've got the manufacturer specification, that's those dark blue lines. You can see that all the data sits nicely within the specification. You can actually see the deviation start to increase at the lower flow rates. That's potentially due to these zero effects, which are common with Coriolis flow meters. But this looks like a reasonably good calibration for all four temperatures, and we certainly be happy with that. Not even that much of a temperature effect either, which looks very, very good. Apologies. So the results look well within specification, so looks good. Now we have high viscosity data. So we have a fluid, it's got a trade name of Primol, so this is just almost like a gear oil. So the viscosity at 10 degrees Celsius is around about 300 centistoke. With increasing temperature, the viscosity decreases and it goes all the way down to 50 centistoke at 40 degrees Celsius. So a notable change in the viscosity with respect to temperature. So what you've got here is potentially two effects, temperature and viscosity. However, this is the same meter as before. We've seen that there wasn't a significant temperature effect, so we can almost solely attribute the effects here to viscosity for this meter, for this calibration. Again, got the same y-axis scaling, kept it consistent with the previous just to show you the deviations, so 0.5 to minus 1.5. Still reference flow rate, and you can see here we've got a clear trend with viscosity. So down here at 300, we've got the largest deviations. Then at 20, the second highest viscosity, we have the second largest deviations, and so on. Bit of a mix between the two highest, around about 50 and 80. There's not a significant viscosity difference there, so that makes sense. Now, there is another way to present this data. If we present it in terms of fluid Reynolds number, so as I said, this is outside of specification, which you can see here. A couple of row points actually within specification, but that's potentially down to zero effects, just by chance. If we plot it against pipe Reynolds number, so we calculate the Reynolds number, which is obviously the ratio of your inertial and viscous forces. I'm not going to go into the equation for that, but hopefully most people are aware of Reynolds number. If you plot it with respect to Reynolds number for the geometry of the pipe, rather than the Coriolis tubes, so this is the pipe Reynolds number, as said here on the x-axis. You can see there's a clear trend with respect to Reynolds number. So this is the same data, this is the kerosene and Primol data from the last two slides. You can see there's quite a clear trend with respect to Reynolds number. So Coriolis meters can be compensated with respect to Reynolds number. If you can infer Reynolds number, you can potentially compensate for it. And there are some Coriolis meters that are now using this kind of methodology. They have it embedded within their flow computer or their transmitter for the calculations. So what does that mean for us with respect to the title of this webinar? Well, this means that if you can calibrate a Coriolis meter for high viscosity fluids with respect to Reynolds number, that means that you don't need to match viscosity. So you don't need to match the fluid perfectly. You can potentially use a substitute fluid at one or two temperatures. As long as you can cover the majority of the Reynolds number range, then you can potentially calibrate that meter with maybe a medium viscosity fluid, depending upon the temperature, and achieve the same Reynolds numbers depending upon the velocities that you can achieve in the laboratory. You could characterize it with respect to Reynolds number. So that's one method that you could use, and I've got some detailed steps here. So the calibration procedure would be this. We would specify the Reynolds number range for the device. You try and match that Reynolds number range with a high viscosity fluid or medium viscosity fluid at two or more temperatures. Just gives you a bit more confidence the more temperatures and viscosities that you have. Crucially, you want to zero the device at operating temperature and pressure. Then you calibrate that device at the Reynolds number as found. You decide if the Reynolds number effect is significant, and if it is, you can then potentially perform an as-left calibration to adjust for that if it has to be the results pulled up slightly or pulled down. In that case, you'd be adjusting the mass factor. So what about gas meters? So that's another real big question we often get asked. What about gas meters in water? Can they be calibrated, and what would you do? Well, first of all, let's investigate the density and resulting mass flow differences, because they are significant. One of the major challenges is ultimately trying to match up conditions. And I have some slides here just to demonstrate what I mean. So I've taken this just from the manufacturer's guidelines. Oops, sorry, once again, just waiting for it to load. It'll load up in a second. Yes, hopefully you can see that now. So what I have here is the liquid flow rates from the manufacturer's guidelines for a 2-inch, 3-inch and 4-inch meter. Now what we're looking at here is the nominal flow rate. You can see I've got the blue rectangle highlighting the nominal flow rate for a 2-inch, 3-inch and 4-inch Coriolis meter. Fairly significant. Try and remember these numbers, but there's not going to be a test on it, so it doesn't matter if you don't get it correct, but they're fairly significant. Let's call the 3-inch mass flow rate 160,000 so 160,000 kilograms per hour. Let's look at it in terms of gas. Once again, I've got my blue rectangle. So this is the same manufacturer, the same meters, 2 inch, 3 inch and 4 inch, the exact same devices. But you can see for mass flow, the nominal gas mass flow rate is a magnitude lower. So for that 3 inch meter, previously, if you remember, I said 160,000 was roughly the maximum nominal flow rate, or the nominal flow rate, apologies. For gas, it's 36,000 kilograms an hour. So that's significantly different. I've got a wee sticker here. It's approximately 20%. If you do the calculation, that's approximately 20% of the liquid mass flow rate. Now, why is that an issue? Well, I'm not saying it is an issue, and it's not, because it's related back to your pressure drop for the Coriolis meter. That's how you ultimately specify your maximum flow. You can see it's detailed above there. I'm looking at a maximum pressure drop of 1.7 natural gas at those conditions. Gives you your nominal mass flow rate. Also relates back to velocity in terms of how high a velocity you can achieve through your tubes, and then certainly with respect to your system and your overall pressure loss. So it is all related, and for gas, it's approximately 20% of the liquid mass flow. What does that mean in terms of operating range? I've created a chart here with respect to that 3 inch Coriolis meter again. So remember, it's the same meter, it doesn't change whether you're using it in liquid or gas. It's the exact same device you will purchase, but it will have a different specification. I didn't include the specification I was going to, but a typical rule of thumb is a Coriolis meter for liquid has a mass flow specification of approximately 0.1. Some manufacture 0.05, but 0.1 is kind of in the range. And for gas, it's in the region of 0.35 to 0.5%, depending on the manufacturer. So for this manufacturer, you can see we're close to about the 0.3% for gas, and we're close to approximately 0.05 for the liquid flow rate. So a magnitude of a difference there between gas and liquid, but also I've overlapped the maximum flow rates. So again, just highlight them with my blue rectangle. You can see liquid up to 160,000 nominally, but gas was only up to, I think it was around about 36,000. So a notable difference. Now, you might think, well, that doesn't matter too much, but it does if you're trying to calibrate it in water for gas use, because what flow rates are you going to calibrate the device? Now, if you're only operating up to 36,000, are you only going to calibrate your device in water up to 36,000 kilograms an hour? Because that's very low velocity for a 3 inch Coriolis meter, and ultimately it means you would be calibrating down the very low end of a Coriolis meter, even though when it operates in gas, it would be operating up the higher end. It's just with respect to mass flow. Now, when I get asked, what do you recommend? Well, I recommend two things. I recommend, yes, you try and calibrate with respect to your mass flow rate. So I would still try and achieve, let's say, 5 mass flow rates down that low end of the water flow. But I would also try and match up respect to turn down. So let's say you're operating from 90% down to 10% of the gas mass flow rate range for your Coriolis meter. That gives you a good coverage. I would then, calibrating in liquid, I would aim to also calibrate it from 10 to 90% of the liquid mass flow rate, the liquid flow rate range. That then gives you both the same flow rates being matched with respect to kilograms per hour mass flow rate, but also with respect to turn down. So I'd have just confidence in the meter performing across its turn down range, but also crucially I'd have confidence in it performing with respect to the exact same mass flow rates. So that's two things to be aware of there. Coriolis meters do work well in both liquids and gases, but if you're trying to calibrate them in gas, then you have to be aware of the different flow range, and crucially you have to be aware of the fact that zero effects are potentially going to dominate some of your results down at the lower end. So as I say, now calibrating a much lower mass flow rate range and potentially have zero effects to contend with. So what do I mean by zero effects? So I have a Coriolis schematic here, obviously exaggerated with respect to the twisting of the tubes, but most folk, well, I'm sure will be aware of how Coriolis meters operate. Ultimately you have a
a driver in the centre that basically oscillates the tubes at its resonant frequency. As the fluid, if there's no fluid passing through, the two tubes oscillate in phase and there's no delta T, there's no phase shift. However, once you introduce some fluid through the Coriolis meter, there's a pick off at the inlet, pick off at the outlet, and with increasing mass flow, you get a larger delta T. So it's more out of phase between the two sets of pick offs between inlet and outlet. That is directly proportional to your mass flow rate. However, in an ideal scenario, with zero flow, you'd have zero delta T and ultimately zero mass flow being recorded, but you don't. You have what's known as zero effects. So as the meter is installed, you still get a slight out of phase between the two pick-offs, and that results in a mass flow rate when there's a perceived mass flow rate when there's zero flow, and this is what the zero effects are. So you want to try and account for these and remove them by performing a zero procedure. So you would check your zero, check if it's out of the specification, zero it, and ultimately this should ideally then account for it. And if you perform a calibration, zero effects shouldn't be significant. Now that's the ideal scenario. However, in most scenarios, what actually happens is you still get some zero effects. And down below around about 5 to 15% of Coriolis meters flow range, you sometimes do get the effect of zero, depending on how significant the zero effects are. So I've got some examples of that. That's just a calculation for it there. So the other question is, are all zeros created equal? So I've got 3 different manufacturers here, their specifications for their zero with respect to meter size. I've got 2, 3 and 4 inch for 3 different manufacturers. On the y-axis I've got that zero stability, so that's the maximum permissible zero that you should be looking to achieve for a suitable operation of your device. And you can see that it varies significantly between vendors, but also varies with respect to meter size, partly down to the tube geometry and the specification of the meter ultimately. But point being is different manufacturers have different zero specifications and they vary by meter size. So no, all zeros are not created equally. But the zero terms will be consistent at least, won't they? Sadly, no. Well, not sadly, there's a lot of different Coriolis manufacturers. I've only included 6 here, but to my knowledge there's at least 12 different Coriolis manufacturers. But these are 6 of the larger ones, more commonly seen at NAL and used by industry. Now, they have that zero stability that I showed you in the previous slide. I converted that into a usable term, kilograms per hour. However, they don't always present it in that manner. They often present it in a different term. So they have percentage of maximum flow, they have microseconds, they have pico value, which is just a term used by Hauser for the pipe in, pipe out value, and the difference between the two. Percentage of nominal flow, zero counts, and again microseconds. So straight away you can see that terms are not consistent, and that is quite challenging as well, because if you're used to using one and then you have a completely different model or manufacturer and it has a different zero term, it can be slightly confusing. You have to refer back to the manufacturer's guidelines for further information. So no, the zero term varies from one manufacturer to another, which is a bit of an annoyance. So what effect can it have on performance? So I have some data here where I've manually changed the zero for a Coriolis meter that we've calibrated. Again, on the x-axis I have reference mass flow in kilograms per hour. On the y-axis I have that deviation from the device under test, the Coriolis meter, with respect to the reference. Here we have set the zero as 0, so ultimately I've applied no zero correction at all. So, and this is the data. Actually looks okay by chance. That's not quite as expected. When I was performing these tests, I was kind of hoping to get larger deviations when I set it to 0, but by chance it looked like this 0 must have been relatively close to being 0. So this means no zero was applied to the device. It's not recommended to do this, I just want to stress that. I then set it back to the factory 0. So what do I mean by that? Well, when a Coriolis meter is manufactured,
the manufacturer performs a zero in their facility. They have their own water facility. It allows them to get their calibration factors as well, factors for ultimately correcting for the device, but also allows them to ascertain basically how good and how stable a device is. They do that factory zero. It's always good to compare that factory zero with the zero that you are determining in your installation, because it should be fairly close to it. You don't want a significant shift. It should hopefully be fairly stable, giving you more confidence that it's a very good meter. When I reset it to the factory zero, you've seen it was outside of specification, which again was quite surprising, but we were at elevated conditions here, so maybe that had slightly affected the zero that were being perceived. Again, this is the zero manufacturer measured in the factory. It's not recommended for use. I'm just doing this to show you the effect of not correctly zeroing your device. Now I use the manufacturer recommended zero procedure. So we followed the procedure as detailed in the manufacturer guidelines. You can see that the results were okay, but actually had a bit of a spread, not too repeatable. I think this calibration maybe wasn't a perfect calibration. I think there was potentially secondary effects going on with this one. This is actually the recommended process, but it just so happened it wasn't a perfect calibration that was performed. Now, if you remember back to that slide where I showed you the zero stabilities, that gave you the maximum permissible zero. Now, I only had it in the positive direction, but you can multiply it in the negative direction. And what that simply means is a Coriolis meter is bidirectional. Ultimately, in our diagram, let's say we're flowing from left to right, and that's forward. You can actually set the device up for reverse flow, and you can flow from right to left, or you can have it bidirectional, where it could flow in either direction. So that means the zero can either be positive or it can be negative in any operation, because you have your inlet pickoff and outlet pickoff. If the inlet pickoff is greater than the outlet pickoff, you'll have a positive zero. If the inlet pickoff is less than the outlet pickoff, you'll have a negative zero. Now we have our max permissible zero, and I've set it to the positive version for this, and you can see the results again. They're not great. Out of specification for various points, quite a lot amount of spread. I then set it to, again, just to stress this is not recommended, I then set it to the maximum negative zero, and once again, out of specification, the results were actually worse than the positive zero. So why am I showing this? Well, I want to just show you that zero has a significant effect on performance. If you're operating a gas flow meter, remember, this is a 3-inch device, up to 160,000 kilograms per hour. The gas flow range was up to nominally 36, so up to this, I included an extra point here, but up to approximately here. And you can see that the zero effects are dominating, and we're down at about 0.2% deviation at this flow rate, and 0.6% here. That's out of specification even for potentially a gas flow meter at these flow rates, and close to it at these flow rates, because the zero effects are starting to dominate. So this is a calibration in liquid. If you were to use it for gas use, I think, in my opinion, some of the performance is basically muddied by the fact that the zero effects are potentially influencing the performance. Now, if you're going to try and put a curve fit through it, which I certainly wouldn't recommend, Coriolis meters shouldn't really be used with a curve fit because they're inherently linear devices at the upper range, then you're going to have significant deviations, and you could be correcting for the zero effects that might not be present when you install it and then check the zero in your installation. So I hope that you understand what I mean by that. Ultimately, if you calibrate the meter in a laboratory and then calibrate it, or check and then calibrate it in your installation, the zero will differ, and as such, those different zeros I was showing you, they clearly affect the performance of the meter down at this flow range, and that means that the results could be completely different. So you're expecting this kind of performance, for example, and then when you install it, have a different zero, the results could be sitting up here. So that's why you should certainly be aware of using a Coriolis meter calibrated in liquid and then trying to use it in gas with a completely different zero. Ultimately, it's certainly challenging and maybe not always recommended. So what are my recommendations and conclusions? So one of the crucial things for Coriolis meters is to follow the zero procedure. So you should always check the zero, check it with respect to the zero stability,
If it's outside the specification or close to the specification, you may want to re-zero. However, if the zero is very good, then you do not need to re-zero it. So this is all detailed here. I don't expect you to read it just now. It's detailed in the NEL Good Practice Guide for Coriolis meters, which I wrote. So if you want to have a read of that, I recommend it. It's freely available on our website. I'll mention it again at the end of the slides today. So just checking the time just now. So 15 minutes remaining, so almost finished. Just at the recommendations and conclusions. So some technologies can be used in multiple fluids, but not all. So straight away, you can't use all fluids, all flow meters with different fluids. Water calibrations do not fully replicate service conditions, certainly with respect to temperature and pressure. Coriolis meters should be characterised against Reynolds number if the fluid is high viscosity. I've already shown you that high viscosity clearly affects the performance of Coriolis meters. Coriolis meters in gaseous have a higher uncertainty than liquid. Again, not everyone's fully aware of that. They don't expect the same performance. And crucially, you'd have to account for that further uncertainty contribution of a different fluid medium. And at present, I would say there's not enough empirical data to give you a good feeling for the effect of, say, LNG compared to water. A flow meter max flow in gas can be around 20% of liquid flow rate due to difference in fluid density. Zero effects can be significant, so please account for that. And you should match the meter turn down rather than mass flow if possible. And as I said, there's further work required with respect to the performance in alternative fluids such as LNG and CO2. So I mentioned that good practice guide. This is the front cover here. I recommend if you're interested in Coriolis meters, you may want to download it. It's free from the website, so just if you want to search for Coriolis Flow Meter Good Practice Guide, NEL, or TÜV-SÜD, NEL. It's a 15-page document, and it provides advice on zero setting, verification, temperature effects, pressure effects, and also viscosity, Reynolds number effects. So all the kind of components that we're aware of that differ between a calibration facility and service conditions. So I hope you enjoyed it, and I'd just like to take some time for questions and answers.
Hello. Okay, thank you so much for that, Chris. So we've got plenty of questions through on this webinar, so we won't have time to get through all of them, but we will get in contact with you right after, in the next few days, after the webinar, with any answers. So the first one, Chris, is, are there any plans for a non-Newtonian fluid facility?
Yep, that's a good question as well, because we are aware that non-Newtonian fluids are extremely challenging. We have completed some work in the past NEL on non-Newtonian fluids. We built a small scale bespoke facility. It was 2 inch, 1.5 to 2 inch, it could accommodate, and we looked at the effect of non-Newtonian fluid on a variety of different flow meters, and we found the effect to be fairly significant. So that facility could be constructed again, but it's not, we don't have plans just now, but it's certainly one that we'd like to publicise, and if people are interested in testing, it's certainly something we're capable of, so that's interesting.
Okay, cool.
Any other questions?
Yes, so we have, which flow meter should I use when my process contains a lot of sand?
Yes, that's again, that's a good question. We get asked that quite a lot, because what you're really wanting to use there now, sand production, sand often occurs with oil production. Now you don't get nice clean oil in a lot of cases, you have a lot of debris, and it can potentially affect flow meters with moving parts, but also even flow meters without moving parts. The one meter most people assume would be very good for it is differential pressure meters, but we actually found, we had a test program where we had a small erosion facility, again a bespoke erosion facility that we can create, and we tested a variety of different flow meters, turbine meters, and I'll be honest, they didn't perform very well because, as you can imagine, they eroded quite quickly. But we also looked at Coriolis and differential pressure meters. We found Coriolis tubes did start to erode over time, as you can imagine, because there's the splitter and then the actual tubes themselves. We did start to see a variation in performance over time, not
turbine meters. But differential pressure meters, we expected them to be quite robust, but we found that the discharge coefficient did change significantly for Venturi meters. So if I was using if I was recommending a flow meter for sand, I'd want to know how much sand is present and whether you have significant funds so that you can periodically change the meter, because we found that near enough all flow meters are affected by erosion. If I had to recommend one, it'd probably be a Venturi meter because it doesn't really have any moving parts and it's fairly robust, but over time it still would be eroded. So it's something to be aware of. Any other questions?
Okay.
Maybe?
Yeah, so I think we'll answer one more, and then don't worry, anybody who has asked a question, we will get back to you as soon as possible with your answers. But we'll just close off on which flow meter would be most suitable to extremely high viscosity fluids.
Yes, so in the presentation today, I showed data for Coriolis meters, and they do perform well with high viscosity fluids, but they do have a viscosity effect. Other flow meters also have a viscosity effect, and some of them are also quite good. They are turbine meters, and so that's a helical type turbine meter, so it's a slightly different blade design, and they can work up to about 1,000 centipoise, but they are viscosity sensitive. So what that means is, if you are going to use it at 1,000 centipoise, then you would ideally want to calibrate it at 1,000 centipoise. So unlike a Coriolis meter, where I recommended that you potentially calibrate it with respect to Reynolds number, turbine meters and even PD meter, which again is another good meter for high viscosity fluids, you'll want to calibrate at the service viscosity. So not just the Reynolds number, which is much easier and it's also cheaper. You could go to a calibration laboratory, calibrate with let's say a medium viscosity fluid at a calibration laboratory, match the Reynolds number and then use it in high viscosity fluid and have confidence that it will work well. You can't do the same thing for turbine and PD. So it just depends. If your viscosity is stable, then you're looking at either a turbine, a PD meter or a Coriolis. However, if your viscosity varies and you're more interested in Reynolds number, I would look at a Coriolis meter. So hopefully that provides some guidance for the end users.